Okay, great. So, let me get started first. So, my name is Yihan Zhang, and I'm now in the Department of Biomedical Science and Engineering. And currently, I'm the chair of the department at the Guangzhou Institute of Science and Technology. This is a research-oriented school, mostly government supported. And today's lecture is for medical students who may not have a wide, broad knowledge in terms of the basics of microscopy. So this is what the title is. Depending on each slide, I would encourage you, if things are not clear, you may raise your hand or interrupt, or the meeting chat is there, so you can actually ask me anything is not clear. You can ask questions. I believe the interaction would make it more beneficial instead of trying to cover all the topics, because you can find even better lectures on YouTube anytime. So that's my belief. Let me see. And also at the end, hopefully we can have time for question and answer. So, because somehow I do not really know your background very well. All right, let's get started. Okay. So, all right. Let me start with a picture which I made for a review paper actually in a book chapter. So optical imaging, I'm discussing, kind of limit my discussion to light, okay, for biomedical research. So for example, let's say if you guys are interested in, let's say, tumors growing inside the brain, and we need a contrast to evaluate where are the tumors and how big is the tumor growing, then you do need a contrast mechanism. In this case, we were using bioluminescence. So tumor cells actually emit light inside the tissue. So you can actually detect it by light imaging. And that is a so-called macroscopic, because it's you're not talking about cellular level, but the tumor tissue level. So that tumor may be sitting in deeper, while your resolution is actually poor. But you want to see something more inside, a smaller scale. For example, this is a picture coming from so-called photoacoustic tomography. And you may be able to see some big vessels with different color, which indicates oxygenation level. So in this case, the scale is like a millimeter scale, and you can achieve some of the contrast mechanism. In this case, functional imaging. But when we talk about microscopy, this is really about micron level, and that's what you may know already. Like cellular scale is micron. So this is an example picture showing blood vessels and very small, like even capillary vessels. And there are some small, sorry about that, but the green color is coming from GFP labeled tumor cells. So the cancer cells express color so that you can actually see whether cancer cells growing. And this is at the scale of microscope. You can actually see individual cells. So between these, we call it mesoscopic. But the real entity of, let's say, what you are interested in, neurophotonics, and you are talking about neuron, which is a neural nerve cells, and the neurons are communicating each other via so-called synapse. Okay, so but those synapse or dendritic spines are tiny, even sometimes micron or less than micron or nanometer scale. So there has been a revolution in microscopy field to look at the level of nanoscopy, let's say tens of nanometer scale. So that we call nanoscopy. And in this case, it's tiny, but it actually reveals a super resolution microscope showing dendritic spines. It's very small, but if it gets higher resolution, unfortunately, your extent of seeing things in the depth is actually shallow. So in this case, less than 100 micron. So that shows a trade-off between if you want higher resolution, you may not be able to see deeper inside the tissue. I think this is a kind of basic want to know. So I want to start with a cutting-edge microscopy. So here, like seeing living cells inside the body. This actually made a cover of Science in 2018. In fact, this technology of a was developed by Nobel laureate in 2014 for the development of super resolution. So let me play it once. I hope this all works. So system correction, and you can see this. So these blue dots are actually some kind of sugar molecules, and these are dendritic cells. Those are uptaking these blue particles, and this is a real time in the multicellular organism. So, and you can see an XQG resolution of the structure of the tissue. And here it's coming, yeah, you see some kind of blobs, which is passing by cells. And so, yes, the immune cells, blood flow, and even mitotic, so dividing cells can be observable. So this is actually a good example of how much of the advancement in microscopy field has come, because you can see very much detail of these cells, and even you can analyze this neutrophil, the immune cells movement, and you can actually see their speed, and you can analyze it all. So this is something like what's happening. This is already like 5 years ago. You may imagine like what's happening. It's the field is fastly coming. So for that, I want to apply today's lecture. So understanding the nature of light. And the second topic of light and tissue, I'll actually skip this because I don't think we have enough time. But I want to discuss with you about geometric optics in imaging. And I will introduce what's optical microscopy and what are the underlying key concepts. And when we are dealing with image, we have to say what's important in imaging as the imaging characteristics. And in fact, what we are seeing is the contrast. So I want to discuss this. If I can finish it like on time, and if you are happy, if you want more, maybe I can move on to the next topic, but I think this by itself might be good enough, but it all depends on whether what you need. And also many figures are coming from here. All right, so let's see. Sorry, this presentation was actually prepared for Korean students, so I have some Koreans there. How many of you can read Korean? Probably not. Yeah, that's totally fine. English is here. So first, when we try to understand, okay, someone has a raise your question. Yeah, understand Korea. That's good. So we are dealing with light, and light is an electromagnetic radiation, which I hope everyone understands. And there are very important some characteristics such as refraction and dispersion, diffraction, and interference. And we sometimes use the word called scattering. And scattering is when this radiation, light or sound, are interacting with some particles or obstacles or changes in the media and change their direction from original straight trajectory. So it sounds a little weird, but it's in physics field, you may remember that like particle hit and then change the angle, and that we call scattering. But I would emphasize all of these phenomena maybe belongs to more of a light scattering in more general term. So I'm going to discuss about the light first as a electromagnetic radiation. So let's say there's a sunlight, and sunlight we only can see are able to see our visible range, which I put it as a rainbow color here. And that's the wavelength we are usually used to be. So visible light is about 400 to 700 nanometer. And but there are also shorter wavelengths or more powerful energetic photons are there. When I say photon energy, which is energy is hc over lambda. So it's like a little confusing, but the point is the shorter wavelengths, the higher energy. That's why you have to avoid UV for preventing skin cancers. And so this is a ultraviolet, or even shorter ones we call X-rays. Even shorter ones we call gamma rays. Very, very powerful one. You can find it from like nuclear weapon or like those. And when it gets longer, we call infrared radiation. And microwave, you can see that can be wavelengths, can be even centimeter. And radio waves, the wavelengths can be even like a mountain, skyscrapers. So all of these are electromagnetic radiation, and we call light usually invisible range. Hopefully this one makes sense. So these depictions are the size of wavelength. All right. So for the light wave as a wave, you guys will be familiar with your basic mathematics class, that the waves can be described as the wavelength and also the phases. Phase means the same wave front in relative to another one. Okay. So here one point of the light waves is if the wavelength, or on the other hand, we call it color. So if it's the same color, we call monochromatic. But like sunlight composes of, in fact, various colors, we call polychromatic. And the invention of laser actually made a big impact. That's why it got Nobel Prize. And many of us in modern microscopy use laser because we can create coherent light, meaning that the relative phases or the wavefront phase relationship can be well controlled. That's a coherent light. And when the light's coherent, we can make it collimated, meaning that we can make a really parallel light, which like you can imagine a laser beam, okay? While another aspect, many other lights are incoherent, and those coherent is hard to make it go very far as a beam. So some of these properties are being used for when we are creating microscopy. So I would say the light wave propagation, some of the key characteristics are chromaticity, which is about the color or different wavelength. Another one is polarization, which is a little far. When electromagnetic wave propagates, there's an electric field oscillating. If that plane we call polarization, but if that's a all consistent in one direction, we call linearly polarized. But if it's a random, that's non-polarized. In fact, the light from the sun is actually non-polarized, while laser light is mostly linearly polarized. And as I say, oops, sorry, the coherent property of the light is that if we can control phase relation well, we call coherent light. But this is a little difficult concept, but you can remember laser light is very coherent, and that can make it as a beam, and we can utilize this for microscopy. All right. I'm not sure whether, have you ever seen on the sunny, hot days, you can see this very strange, there's no water, you can see, raise your hands, have you seen of this phenomenon? Okay. So that's a mirage. And this is coming from the refraction property of the light. And I can say the air, what the ambient air surrounding us has a refractive index. And when there's a hot weather, the air expands and the refractive index lowers. So cool air has a high refractive index, but when the light propagates, they tend to move from warm to cool air. The reason is it's more higher refractive index. So this is how you can see mirage, because, for example, in the desert, you can see this virtual image because we do not know until the light comes into our eye and we recognize that this the trees are actually here. That's what we are seeing as an illusion. And I have to say, in daily our lives, what we are seeing and recognizing, perceiving the world could be all illusion too, right? And the same is true when the nighttime. And if you look at this glass of water, and you can see this straw is angled, and that is coming from the refraction of the light. And in fact, there's a Korean old saying that birds listen to your talk during the daytime, and you can see that this talk is about not light, but sound wave, but both are wave. So if the birds are here, they can listen your sound actually very well in the sky or higher. And the rats listen during the night, because if it's night, your sound actually travels to the ground. So the rats, so I don't know whether our ancestors knew about this refraction phenomena of a wave, but that actually was very interesting. Let me talk about showing about the rainbow of double rainbow. I'm not sure. Anyone have seen double rainbow? Raise your hand. Okay, great. You guys are having much experience. What's interesting here is you look at the rainbow, we usually know that this red, blue, and green and blue, this order. But something interesting here, another one, the order is reversed. So when I look at the Korean artist who draw a rainbow with this one, I was upset at first. Hey, this guy do not even know how the rainbow looks. But afterwards, I regret because there exists this actual rainbow. So that is, in fact, can be explained. And you can see, depending on the raindrops and the angle of the observer, this can happen. Okay, where comes all of this is because of dispersion of light, meaning that the speed of the light can be different from different media. So, for example, you guys all probably know, or the light prism can split the light into various colors. In fact, what that means is the light, visible light, white light, composes of different colors or wavelength. But different wavelengths has different speed or different angle of refraction. And that speed ratio we call as a refractive index. This is a basic concept for understanding refractive index compared to the speed of the light in a vacuum or in a medium. Now, why is it important? You can see in that later. But the point I want to make is with different color, this refractive index or speeds can be different. And that phenomena we call dispersion of the light. Usually it makes us a little difficult for imaging multicolor, but at the same time, this allows us to see a beautiful rainbow as well. Okay, I'm sure you guys, does the Turkey have a ocean in your country? Sorry, I do not know much about your
We
country.
don't have oceans, but we have a lot of seas around over here. So we also that
Okay,
kind of scenes before. Yes.
great. I hope you guys at least see some of this phenomenon by yourself. So the wave comes in, hits, and you can see this beautiful round. You can see, I think this is a human, so the scale is huge. And when we see this, we call a diffraction while passing through a gap. So what I want to emphasize it here is the light. In fact, the visible light, the wavelength matters. The wavelength is about 400 to 700 nanometer. It's tiny for us. So that's why we can see that tiny object by using microscopy. And at the same time, this diffraction, which is a universal phenomenon for any waves. So here is actually it's a water wave. It's not light, okay? But another is even sound wave. Like when I say this voice, you can hear it from another room, even not direct. How? Because the waves actually diffract or bend itself. So that phenomena is very universal. Unfortunately, this puts a limit for us to see small, tiny objects. So this put a fundamental physical limit for us to see really tiny objects that we call diffraction limit. And in fact, this set us about if there's a wavelength of this size, then we cannot see half of this size because of diffraction. But this was broken recently, in fact, that, you know, our 100 nanometer is usually the diffraction limit, but people try to make a trick to avoid this, to make it 100 into 10 nanometer scale. That's why they got Nobel Prize like about 9 years ago. So that's what I will emphasize. So, but we better to understand what's going on about this. When I say diffraction of light or diffraction of wave, it's all about interaction of this wave. When I put these lines, this line is actually the same phases. Let's say when the wave is there, like this wave fronts, when they interact with this, they will start to bend. But when they interact with the tinier holes, they actually bend more. This is what I want to emphasize. What matters here is the wavelength versus the size of the aperture. So all this is in fact relative now. For example, if I have using the same size of aperture, but with a longer wave, what you can see is the bending is actually more. That's what I want to emphasize for you. So diffraction is sorry, I cannot write it down for you, but I hope you understand. It's the bending, B-E-N-D, of waves around an obstacle or through a hole here. Okay, so the effect of diffractions are greater for longer or shorter wavelength. So let me ask maybe Denise.
Longer.
Okay, great. In fact, I have to say relatively longer because it's all relative. And diffraction effects are greater for relatively smaller holes. So that hopefully this one makes you understand. Because if the light is like all moving without this diffraction, in principle, what that means is we can have a very high resolution. But all these lights are wave. Even electron microscopy, which you guys may encounter, electron is not a light, but it's a tiny particle. So, you know, in physics, even electron has waves. It's called matter wave. But electron's wave is so tiny that we can achieve even higher, let's say nanometer or angstrom level resolution. That's why you guys will use electron microscope to see really small, tiny detail of subcellular organelles, or even like synapse and those. So I just have another example of diffraction phenomena. So there's a slit, and you send the light and you put a screen here. What you see over here is a kind of a rainbow pattern, but what matters for you is the white is the combination of all this, let's say, red, green, and blue colors. So that makes it white, but somehow they are spreading here. And I just want to show you the example of decomposing the white light into red, yellow, green, blue. So you can see the blue is the least amount of diffraction, while the wavelength goes longer and longer, like red, it spreads more. And maybe some of you have eyeglasses. You could find this phenomenon even in your eyeglass to watching, let's say, a fluorescent lamp on the little oblique angle, you will see this. Okay, so another concept of light is a polarization. This is only another aspect of the light when there is I didn't cover you about electromagnetic field much, but this is the electric field, but it can be composed of many different angles. And just for practical tip for you is you may want to use sunglasses which is polarized, more expensive, but it helps you in the blocking light. And the other is interference of light. So everyone probably knows soap film interference, which is called a thin film interferometry. And I guess you guys know abalone shell, which is beautiful color. What matters is this color is not coming from the material itself. Typical red, blue, black, white color from materials are due to the absorption of selected light, so that only the other lights are reflected to enter your eyes. But in this case, this is nanostructure, which creates a different interference, which gives us a beautiful color. And why is this important for microscopy? Because we can utilize this interference based on constructive or destructive, depending on different colors, which gives us this different patterns. And we potentially use this one as a microscopy. So that's the basics of microscopy. And I'm gonna just summarize you here. Reflection and refraction, dispersion, diffraction. This is most important in light microscopy, especially for resolution, and polarization and interference. Hopefully, that gives you first a general overview. And I'm going to skip the light with the tissue because that's probably another topic. Now I'm going to enter into optical imaging concept. What you are seeing outside of the world is due to there's ambient light hitting the object. Even you are seeing me because of the light hits me, and then all this scattered light from each point somehow focus back to your eyes or your retina, and we call that as an image. So, but this scattered diverging light has to be converged. And we need to do something that's typically a lens. And that's actually the phenomenon called refraction. And I'm sure you've learned so-called a Snell's law. It's just a bending of the light depending on refractive index change. And a famous one for doing this is actually a lens. So this is just for fun to you, for survival skill. And in fact, when you try to spear fishing, you have the fish looks shallow, but the fish is actually deeper. So you have to put this one to actually catch it. So that's the refraction of the light. And I want to show here a point object, light scattered, your lens. Actually, in your eye, you have a very similar like this, a simple lens that will refract light to make into a point again. So that is we call point images. If you have an arrowhead will be the scattered light will be converged into a point. So this one's a real image plane. In fact, your retina recognizes as a 2D image mapped into another 2D that we call optical imaging. That's how we see everyone outside of the world every day. In fact, in our retina, there's a flip upside down. So that our eye is, I think the camera is mimicking our eyes. The important point here is iris, we have iris diaphragm, which controls the amount of light. And the camera has now CCD sensor or CMOS sensor nowadays. Your all phones has a CMOS sensor that is a retina. So going back to optical system again, there's an object, light scattered or coming out every single point, and you somehow use optical elements to map back to 2D that we call image. So this is a simple imaging, each point of the object mapped onto single point in the image. But if this is something like true, then we will have infinitely good microscope. And the reality, it's not the real. Okay, so in real world, image system do not focus perfect. Even your eyes do not focus perfect. That's why you cannot see molecules with your bare eyes and cells in your bare eyes. Why? As I pointed out at the beginning, let me see, Surah, can you answer try to this?
Actually, I don't know, sir.
Aha, okay. In fact, this is diffraction. The bending of the wave phenomena do not allow us to have a perfect imaging. So it's a diffraction, limited resolution. In fact, this is a fundamental limit people believe for hundreds of years. That's why we got Nobel Prize by showing we can overcome this limit. And the other is just our lens is not perfect, and that we call aberration. And to define imperfection of the image formation, sorry, the spelling is ABERRATION, okay? And so this all is really why we cannot have a perfect imaging, and you have to be aware of the limits, okay? And let's going on a little bit of a geometric object. I'm sure you will not be building your microscope at this point, but this is a kind of a, what I just say, when you have a one lens and imaging, the light propagates, the lens has a focus. So when it goes parallel like sunlight, it will go to the center through the focus. And the same point, there are multiple lines, actually but you want to find the key ones. For example, like that pass to the center will not deviate because it's symmetric. And the other one, when the rays passing through the focus of the lens, then they will be parallel to the optical axis. So this way, you can actually find out where comes the image formed. And we usually have this geometric optics. You guys know from the geometry, what you can find is, if you have a lens with a focal length f, and if you know the objects is apart from d0, you can compute where will be the image and what will be the size of the image, and that ratio we call magnification. So that's kind of the basics of geometric optics of a microscope. But in modern microscope, actually have not only this one lens, but multiple lenses, so that we can apply more tricks to improve. So that's how I want to introduce you to the optical microscopy technique. So here's the history. It's good to know a little bit in the beginning. In fact, it started from Dutch Netherlands, von Leeuwenhoek microscope with just one lens. It's hard to see the lens, but microscope, this has a simple magnifier with a Johann Ham, an assistant who first observed human sperm. So you can see here, we call homunculus. you cannot see human sperm, and they assume that there's a tiny person here. Why? Because it wasn't perfect. Okay, so people have used more multiple lenses to have Hooke's microscopes, which we call compound microscope. And tiny one, you need to somehow illuminate, and then you start to see even smaller objects and even living things. So, for example, like the cork, the plant they observed, and then first name the cell you guys are using for cell. In fact, cells are used for jail, the room for the criminals that used to be, and then Zeiss microscope has come. All right, so this is a little more technical, so I'm gonna move a little faster. But the point is, when you are using microscope, you have this lens formula. In fact, the lens makes an inverted image, and you have an eyepiece. And in fact, your eyes contains another lens. So you can see the light coming focuses onto your retina. And that's how you are using a microscope. But this is an old one, I would say. Modern microscope usually use at least two lenses we call objective lens. And because there's a tube here, we call tube lens. Then because it's a focus, the rays will be in parallel in between, and they focus down to form an image we call intermediate, and you have an eyepiece, and your eye will look at. So now it flips again, so you are looking at this object. This is why when you're looking at some microscope, sometimes they move on the opposite direction. Okay. And another parallel light beam here is, in fact, give us a very good opportunity to manipulate the light so that you hear various kinds of different types of microscope we are utilizing this. And we call this as an infinity corrected, or because it's supposed to run infinite space. All right, so when you are in pathology class, people are using these types of bright field microscope, the simple one, and your pathology slides are giving contrast from absorbance. So it contains actually color, and so histopathology. People are working on that. But when you are working in a laboratory, modern microscope actually looks more complicated, but the basics are exactly the same. Objective lens, and there is a tube lens here. And then it gets into your eyepiece. And another path is to giving an illumination, or called excitation light, for fluorescence microscope. So we'll get back to this again later on. Okay. So now I'm gonna, when you are using microscope, you may have a question about, especially important thing is the resolution. So this might be a little difficult, but I hope you guys understand. Then you will be able to tell about microscopy with someone else. So what I want to say is, when you are, let's say, going outside, let's say soccer game, you see the reporters have a huge, very big zoom lens. What does the zoom lens do? Is making a more higher resolution or magnification with a very big lens, very expensive, but let's see what makes that difference. So we call that this angle, the amount of angle contains the information coming out of the sample. So you are accepting this information into your optical system. And so this angle matters. And also another important thing is the media between sample and the objective lens. Usually that refractive index. Usually it can be air, but for higher special microscope, you're going to use water immersion lens or even oil immersion. Why? Because this gives you a better opportunity to have information content we call numerical aperture. First, it might sound a little weird, but this is defined first by Ernst Abbe, and this is dimensionless, and that number determines optical resolution. That's why. So if you want to increase your resolution, you want to increase the angle, or you want to use a big lens. That's why bigger lens is more expensive if given the same distance. And how does it different? Look at that low numerical aperture or low angle versus high NA. So if the lens sizes are different, as I say, imaging is not perfect. Point become point, that's a perfect imaging. But in reality, point will be blurred. So this is a depiction of the profile. And if you have a higher angle, you will have a sharper ones. So this is the real image in your photo detector. Okay, so what they say is larger numerical aperture that collects more light. If you love photography, they will use a shorter exposure time, or we call it camera speed, okay, because it collects more light. So it's brighter, but what's actually more important thing is better lateral resolution. At the same time, you will have a nice blurring effect on the different focus that you guys knows. So high NA will focus very well, but that means it blurs in out of the focus. So for us, very aesthetic effect can be expected too. All right. So some of the microscope, you're gonna use the water immersion or the oil immersion. And let me try to explain you why. Here you can see this is objective lens, first lens, and you have a specimen, let's say cells, and you have a covered glass. The thing is, when the rays, lights going from high refractive index to low refractive index, they may bend through and going outside. So you will not able to see this information. However, if you feel this without air, but let's say this is oil, which is refractive index of 1.5, you know, glass refractive index is about 1.5. So they are made to be the same. Then those rays, which used to be go outside, is now captured through your optical system. You gain more information, giving you higher resolution. So that's why this numerical aperture actually have the N over here, refractive index of the emergent media. So here, this is a reality of the picture. In fact, this is so tiny that we call working distance from the tip of the objective lens to the cover glass. That is, in fact, in this case, 230 micron. So you guys should not approach to break expensive objective. You guys go closer and always moving backwards to focus, right? So here, how to increase resolution? The point is, you either use that emergent media with higher refractive index, or you want to use objective lens with a higher angle, bigger angle. So that's how you can have a higher resolution. So this is just a point source. If you have objective lens and tube lens, this is what you see. This data is actually I collected. And when we call this one from the top, it looks like this. So that's why it's named as airy disk. Let me give you a rule of thumb of the resolution here. People already worked out 0.61 lambda over NA. Forget about 0.6, but resolution or the diameter of this first peak is actually about half of wavelength. That's what you want to remember. So what you can see, light or wave is a ruler, the wavelength, and if you have a ruler, maybe you can distinguish about half. But it's divided by NA, meaning that if you have a higher NA, you will have even better resolution. So that's what point becomes your image, which will be spread. So we call this as a PSF, or point spread, SPREAD function. That function is more coming from engineering concept. So that's what I want to say. What does this actually mean? That you will not be able to distinguish smaller object than this. So definition of PSF is the image of self-luminous here. Point object is a, why it become blurry? Because fundamentally it's a diffraction pattern, an interference pattern created by action of interference in the image plane. This is a more fundamental understanding of how you are actually looking at the point. And important thing I want you to know is, like, let's say your molecule of protein size could be 10 nanometer. Or some of the organelle size can be 100 nanometer. If you look at this one with a typical microscope, which has a resolution of, let's say, 500 nanometer, they will all the same. This is the point. Even if the object is small, what you see the smallest is 500 nanometer. That's why we cannot see the fine details if it's smaller. And hopefully you understand the concept of point spread function here. And I already showed you NA and spatial resolution. With low NA, you have a poor point spread function. High NA, you have a narrower point spread function. And we need to say everything quantitatively to communicate each other. Hey, what's your resolution? So there comes a define resolution, meaning coming from resolving something. So let me show you 2 points here. You guys can readily distinguish, but when 2 points are closer to each other, they start to stick together. And here, you will never be able to say there will be 2 objects or not clear. So that minimum distance, you can distinguish, we call spatial resolution. That's how we define it. And one easy way is, because it's interference pattern, the top to first bottom, and this top to first bottom, that distance is easy to define. That we call Rayleigh resolution. Okay. All right. So, but in practice, when you're taking image, the lower part, which is a low, there are going to be a lot of noises. So this original definition is hard, so that you can just define the bottom to top, and full width, you just make the half cut, and this distance is practically what we are using when we call it resolution. So when you're communicating with others, this is how you want to use. All right, imaging characteristics. And whenever you are dealing with an image, when you read the literature, or when you're making an image to report, this is an example, this 6. Actually, I made this one with my own sample, and what matters is, when people look at this, they may not say, hey, is this a rat or a mouse? And you guys know they are very different size. One can readily say, hey, this is 1 centimeter, hey, that must be a mouse. And also, so this is we call scale bar. And with the scale bar, you can readily say this is about 30 plus millimeter, 30 plus millimeter, that we call field of view. So whenever microscopy imaging, you better to have scale bar or be able to tell field of view. So you can see 2 different field of views. Okay, and one thing here is original 10x optical digital. Your digital zoom actually do not provide more information. So that's why optical zoom is there. And in fact, you pay more money for high optical zoom, which in fact optically making your resolution better. That's why. All right. And the other concept you want to say, especially not still image, you want to see dynamic image, then you define as frame rate, usually frames per second. And like our videos, usually video rate is 30 frame per second. And sometimes we call real-time imaging. And what's the right frame rate when we claim of a real-time imaging? Maybe someone can try to answer. Sevar?
I have a question actually.
Sorry?
I have a question actually. Can you hear
Sure,
me?
sure.
What's your favorite microscope and why?
You're asking a favorite microscope? Okay. Good question. That I can show you what my favorite, but I'm actually a microscopist. We're building microscope. So new types of microscope. We are not getting there yet, but let me tell you the direction. So I'm building a microscope for real-time imaging. Okay, here the answer for this is there's no fixed frame rate for real-time imaging. It depends on what I want to see. And in my case, I want to see the neuronal actions in real time, but neuron firing is very, very fast. For example, you guys may remember action potential is about 1 millisecond scale. That millisecond scale to see, you need at least a 1,000 frames per second, which is very much difficult for typical camera. So we are trying to overcome those. I hope that maybe there will be some opportunity for me to share it with you. So, but that's an advanced microscopy. So thanks for the question. But I used to make a confocal microscope, two photon microscope, and those, which I haven't been able to show it to you at this moment. So finally, I just want to give you an idea for, let's say, contrast generation. So this is a more general thing. So when we are calling microscopic imaging, imaging is really process of mapping certain property of an object and display in a visual form because we are visual animals. And what do I mean by physical property? That is a contrast mechanism. Without contrast, you cannot be able to see, let's say, transparent object. So you need to somehow give contrast. That could be, for example, X-rays. You can have contrast due to the X-ray absorption, especially in the bones, so that you can see the cracks, or COVID-19 patients, the differences of absorption. And as I didn't say much about phase contrast, but that's coming from scattering of light. I didn't show you fluorescence imaging, which is very much kind of popular for advanced microscopy with specific molecule or proteins you are interested. And that's coming from emission of light, emission, emission. But
Sir, can I ask a question?
of course, yes.
We also see some immunohistological painting and pathology
Yes.
in our classes. Is it working with emission? We're not learn details in our school, but the emission sounds like correlated with immunohistology. Is that
Okay.
right?
Yeah, I think I understand what you say in histopathology or histology class. Usually you are using hemotoxylin and eosin.
Yes, we also use that, but there is some receptors. So we also use some like immunofluorescent paintings.
Oh, exactly. True. So my answer is for H&E, like conventional stained microscopy, you are not using fluorescence. In that case, you are using absorption of the light that gives a color to you, let's say pinkish or bluish. that's not coming from emission, but because of another colors are all being observed, like pigments. But when you're looking at immunofluorescence, that actually is using fluorescence emission. So that specific molecules are coming. Your question is very, very important for you when you're learning that. So yeah, thank you for the
Thank you.
question. And the resolution versus contrast is, I just want to define. Resolution is depends on the microscope itself, a property. Contrast is not only the instrument, but your sample. If your sample prep is not proper, you may not be able to get the contrast. All right, so I think this is just a simple example of the cells. When you are looking at the cell, it's very hard to see because it's transparent. And why transparent material you cannot see? Because the light is passing through without absorption. This one's absorption. So you need a trick for that. We call dark field microscope. That dark field is making the background into dark by using oblique light. Okay. And the other is a phase contrast. Is a trick that this phase object, if you use a interference of the light, then you will be able to make a constructive and destructive interference that you can actually see things more clearly. No labels. So that's why he got Nobel Prize in 1953 by the invention of phase contrast, by understanding the wave nature of the light. So hopefully you guys can look at a little detail. And in the microscope in the lab, you may have a DIC microscope. Have you ever heard DIC, differential interference contrast microscope? Okay, nobody? Oh yeah, good. So some of the microscope uses, this is a trick by using a prism and that one less than prism splits the light into different and combine to give you a contrast of the unstained phase object. So this is what DIC microscope look like. So if you look at something like shadow in one direction, that's differential microscope. So why I'm showing you this? Because majority of your cells are transparent and you cannot see it very well under the bright field microscope. So we can utilize some of the microscope giving phase contrast object will give you sometimes halo, but give you some good idea. DIC microscopes gives you some 3D looks like contrast, which is helpful. And as a Barak asked, fluorescence microscope, you stain only the organelle of interesting molecules with this color, then you use a filter to filter out all others. You can only see those interesting ones. We call, which is typically used in immunofluorescence microscope. All right, so that's the contrast mechanism. I gave it here, but this is the summary. Summary of light imaging and microscopy. I explained to starting from the nature of the light, the basics, and geometric optics, how we are forming an image. And I introduce a optical microscopy, how imaging can be formed. And then key concepts in microscopic imaging, I actually discuss a diffraction limit and the concept of numerical aperture and point spread function. This is a little advanced, but this sets aside for you to be able to say what limits your resolution of optical microscope was actually diffraction. And I discussed about the contrast, field of view, and frame rate. And I actually skimmed through a little bit of these microscopy techniques. The gray ones I didn't cover, but this is the basics. So I would rather, sorry, it takes already an hour. I would rather getting your question to spend a few more minutes. That would be more, I think, helpful for you. So, okay, let me close. Yeah. All right, this is the time for you. Maybe each of you can ask questions. Or you can use the chatting room, then I think I can try to answer. Okay. Okay. Dennis?
Yes, I have two different questions, but
Yeah.
one of them is that in infinity corrected microscopes, I understand that how it affects the magnitude, but how does it exactly change the resolution?
How to change the resolution? How to increase
Yes,
the
with infinity
okay.
corrected microscope.
So let me bring actually my second. Can you see the screen?
Yes,
Okay. So you're asking about different types of how to change the magnification or resolution of the microscope. Typically, how it.
how to,
Yes.
sorry,
No, go ahead.
how to change the resolution with infinity corrected microscope. I understand the magnificent part, but I didn't get the resolution part.
Sure, I see. Let me see. Okay. Let me go back to see to answer your question. So the short answer is you just change the objective lens. Okay.
With tube lens?
Objective lens. Tube lens is
Okay.
usually common. Let me
Mhm.
show you the other. Actually, that's a good, important question. Let me go back to reveal a little bit of hidden slide. Can you see this?
Yes.
Okay. So this is a objective lens, and the key part of the objective lens you need to be able to read on the side. 60x is magnification, and this slash and numerical aperture here, 1.4 is very high. So you want to have really high resolution, you may use this one, but you put here immersion media, oil. It's a little bit
Mhm.
difficult to use at the beginning, but you're better to use this one. For example, in comparison, another objective, you have a 20x magnification. For histology, this is many people use it for looking at the cellular scale, but you see slash numerical aperture 0.75. So it's a little bit lower. Actually, this number, numerical aperture, determines the optical resolution. If
Okay.
you want to
Thank
have
you.
high, yeah. So you're changing this, but tube length is remain the same. So you are changing the objective length. You kind of remember the nose pieces. Good question. So
Thanks.
yes, there's a Barry. I cannot read this much. Yeah.
Hi, it's Peter and it's fine. Actually, my question is about um, you said electrons are little particles, but they also have waves, and also in neurons there is an electrochemical transmission. So there is an actual electrical current. I don't understand that how these electron currents don't doesn't change the how we see the tissue.
You're
I hope
asking, sorry, there's some noise, but your question is how electron microscope works, like by microscopy?
I'm sorry, I had an urgent matter and I had to go outside.
Sure, no problem.
My question was, you told electrons are little particles, but they also have waves. And for example, to image a neuron, neurons have electrochemical transmission. There's an actual current in a neuron axon. So how this can, I don't understand how this can change, doesn't change the resolution or other properties for us to see the tissue.
Okay, okay, that's very good question because I'm sure you will be, some of you will may use electron microscope, and pathologists also uses electron microscope. But the fundamentals, why I started with a wave, the nature of wave, which is a bending, and we use that bending property by use of lens to scatter the light, to collect scattered light into a point which will form an image. So likewise, electron is a particle, but in modern physics, discovered that these tiny particles also have their own wavelength, which is super tiny. And in fact, the shorter wavelength, we have a, in principle, better resolution. So we can make a electron lens, which is electromagnetic lens, and we use that. Sorry about the noise. Sorry. Sorry about. Sorry. So electron in one aspect can be considered as a very short, having very short wavelength. You can create electromagnetic lens and create electron microscope. Okay. So yeah, this is a little beyond, but that's why you are using electron microscope for looking at tiny inside the synapse. What molecules are there, what kind of receptors are there. But unfortunately, electron microscope do not be useful for live sample. You have to fix it. That's the difference. A light microscope allows you to look at live cells, as I just showed at the beginning, and that's a kind of a big difference. Okay, yeah.
Okay, thank you.
Yeah, sorry,
By the way, it's so cute. What is its name?
Coco.
What is your dog's name? Coco. Hi,
Yeah,
Coco. It's so cute.
he suffers from the cataract. He's old, over 10 years old. So all right. Yeah. So anyone, any remaining question? I would love to discuss with you. Sorry, I didn't have enough time for actually sharing everything. Maybe if not, I can use just for a few minutes to give you maybe how modern microscope look like. Let me, maybe this might be helpful for you guys. Okay. So, I mean, you guys are interested in neuroscience. So you guys all know Santiago Ramón y Cajal. And I hope you guys are all enjoying art because he wanted to become a painter. Everyone probably knows. So that observation is very important to understand and propose about what's there. And this is a retina, and this is hippocampus. And holy grail of optical microscopy, which actually this is Nobel Prize winning work, called the STED microscope, which I didn't have time to cover. But the point is you use a nonlinear trick to having super high resolution. So in this case, tens of nanometer resolution to look at the neurons in real time. As I say, light microscope allows us to look at real-time of dendritic spines. Well, he showed every 6 or a few minutes, that dendritic spine is changing orientation, meaning that they are very dynamic. So our memory formation, for example, our neurons are working very hard, not only metabolically, but they actually keep generating, connecting with, communicating with another neurons for information processing. So that Android explained. And I didn't cover you about two-photon microscope, but I have to say, microscope, you cannot see microscopic resolution in very deep, say, let's say several hundred microns. So a trick to make the whole brain is you take some image depth and you cut it out and you take another, cut, take a picture, cut, and you reconstruct whole 3D at the cellular resolution. You may heard about Allen Brain Institute in United States in Seattle. They provide you whole map of this, okay, by using serial two-photon tomography. In fact, this guy used to be a postdoc in our laboratory who found a company called Tissue Vision when I was a graduate student at MIT. And another big thing is called clarity, which was exactly 10 years ago. There's a concept when I say scattering. If you want to make any tissue into transparent, then you don't have to worry about scattering and your imaging can be very clear, right? So here's a trick with hydrogel, and light scattering lipids can be taken out by electrophoretic clearing, which hydrogel is the component of your contact lens. And this allows the whole mouse brain, which is not clear, not transparent, but afterwards, this can be this clear. So after what you can see through the brain, which of course, in this case, fluorescence microscope by using confocal microscope. So you can see inside the brain, each individual cells labeled with fluorescence and their collections, let's say, here. And these are like, I guess this is a brainstem, which leads to the spinal cord. And so at the exquisite resolution of a cellular level, this is already 10 years now, it's commercialized. So you could actually do this by yourself with buying proper apparatus. So there are companies which now are giving you the sense, especially for nervous system. I know you guys are interested in neuroscience, and these technologies development, in fact, allows us now, let's say you're interested in Alzheimer's disease, and you can generate a hypothesis. Where comes the amyloid beta accumulation start? You could use this technology to find out, hey, the Alzheimer's amyloid beta start to accumulate in one place to spread out. Maybe this is the mechanism we may target. So those, important hypotheses can be coming out of this technology. And of course, super resolution microscopy, as I said, a Nobel Prize winning concept has come out. And this is kind of some principle we call palm or stone. But I think this is okay for today. What I want to share is what's our up-to-date technology. Whole brain. Unlike electron microscope, while resolution is less, but we can have a live animal. Our dream is every single neurons inside the brain, how do they generate, communicate, so that allows us to understand our emotions and our memory and our daily thinking, what's happening in our brain. We cannot do in human first. For zebrafish is a little transparent. So here's an example of the 3D real-time view of a blinking spot. This is calcium imaging at single cell resolution. But unfortunately, we do not decode or understand what's going on. But we do know something's going on. Look at that firing. When we show zebrafish eyes, some screens and some object, then the zebrafish whole brain cells are responding like this. But this is big. You put the zebrafish in fixed mode, like if it's human, will be a lot of stress. So this was actually 10 years ago. Now what happens? This is like afterwards. now we want to see more natural state, what the this zebrafish, while they are looking for prey, what happens in their brain. So this technology is now possible. Look at, there's a phrase, they change this. While during their natural movement, the brain, this single cell, when they capture the food trays, their brain activity changes. Unfortunately, we do not yet understand exactly what's going on, but the technology of microscopy allows us to look at this. So, and this is actually what I did in optogenetics. So when you are putting these optogenetic genes in the motor cortex, if you shine the light, the animal will move their limb, so they will automatically move. Look at that. On, they move.
Yeah. So, but it's keep up.
Okay. So that's something. Now we are using the light optogenetics to control the movement of animal. This is an example
Yeah.
of
Oh, but it's keep
optogenetics.
on. Oh, no.
So,
I can just watch
like, this is an experiment,
And
and
I can hear it too.
you can actually analyze each of
Yeah.
single cell
And
responses.
also, I want to
Yeah.
see whether the whisker, the
And this guy is the inventor of optogenetics at Stanford University. And I think those you are interested in neuroscience probably knows what's optogenetics. All right, so yeah, that's all. Okay, sorry for taking more than an hour, but I hope some of these may be helpful for you guys to pursue your medical training. And we still do not know a lot of things and this problem. And I hope you guys will be someone who can invent some of these new ways of technology or understanding and utilize the technology. Okay, guys, maybe this I will stop sharing. That's right. Let's see. Stop.
We are really thank you for you, sir, because we are all interested in neuroscience and we always wanted to work in laboratory and we make some different research. So understanding fundamentals of different microscopes is so important for us.
Yeah.
And we understand the fundamentals and I hope we can make further research and studies in the future. So thank you for this so exciting. Your lesson was really exciting and really helpful for us. For you, we are really thankful to giving your time to us.
Okay, yeah, it's my pleasure. And you know, who knows, if you are really interested in research, you can come to South Korea.
We really want, actually.
Yeah, actually, I had the like physician scientist coming from Egypt, and I have two dentists from India. There are above actually students from physician training who are interested in research. There's an opportunity. So you guys, you guys can contact me later. And I hope you are not you enjoy the lecture, and I will try to send you that, make a YouTube link, and so that some of you may be interested
Thank you.
can review. All right, guys, let me take another picture over here.